this coming live report. Are we? I think.
PCM maybe?
I thought that was listed on the assignments.
And then the next one's supposed to
I
be
flew because I went to the zoo.
EAK?
Ask
ASK?
one.
Yeah, that's right.
There's ask and fsk.
It's different.
Yeah.
I think it's just binary representation.
Yeah.
I was happy with the homework though.
Yeah. The quantization one, that's actually like kind of easy to follow. Yeah.
So on the first one, did you guys do 0.5 triangle? Or did you start with just triangle, 2 triangle, 3 triangle? I can't remember what the step size was. I can't remember what it was.
Oh, I didn't. Oh, maybe not. I didn't draw anything out.
I didn't draw anything, but as far as like.
Saying, yeah, saying triangle, and I was like, I think I know what you're talking about. You're talking about that one diagram that goes something down.
Henry Lee, Elisha Parker, Dylan, can you pass it over? Sorry. Tino,
Thank you, sir.
Joe Butler,
He was like in the Mitra,
Yeah.
in the same letter would go up and then over
Ruben.
to 1.5.
Yeah.
you made it back.
I probably should have done better about
And then the other one,
specifying all that.
and then the other one, I think was
Sino,
triangle. Sino?
Nathan Evans,
Okay.
okay.
I
No, I
tried to
think that
confirm with
was
somebody.
pretty close to generally what I've got, I think.
What is this?
Yeah, I think I got the same numbers as you.
Homework.
Homework, oh.
Oh, yeah.
Who's teaching it?
Drew Addison.
Yeah.
He's taken for Tagnet during the summer.
Yeah. I think I saw some of the same numbers that I've got on here, so yeah, you're
As long as
good.
that's,
Yeah.
I think they'll appreciate the effort either way.
Yeah. Put way more effort into that. Mine's all on like one page. It's only equations.
I always try to teach myself on the homework, which may be an issue. That allows me to understand it when I'm
Wait,
going
what?
back.
don't know where the college
I always try to teach myself on the homework.
Well, I was watching the
Going
game.
back.
After it was about 6
Something.
That's about right.
It was tough to watch.
Lost interest. Yeah, we got pulverized.
What, last night's baseball game?
What was
Okay.
the final score? 11?
11-1. We scored one.
We did
so,
get a home run.
Yeah.
I flew back yesterday before that game.
Dang, dude.
Well, that's the furthest we've gone. I think ever. I think. But I could be wrong. I don't think we ever made it further than that. It's kind of interesting because when I got here, football was the program. Then along came Bruce Pearl. And then basketball, we almost made it to the finals, but we went to the quarterfinals or semifinals. And now with this baseball thing with Rich Johnson, who knows? maybe these guys are going to battle before we do
And the
football.
gymnastics.
Yeah,
Yeah.
gymnastics. We got a gold medalist. I don't think. I remember with swimming with Marsh, we won title after title. But Marsh, the track, I don't know how he did it. He got swimmers. All these guys basically were gold, silver medal categories. And there was one person named Allison Bach. I'll never forget. She was a freshman, and I used to swim with masters. So we go to the pool at 5:37 to 6, and we'd swim sometimes. And the swim team would be there before us. And she could go underwater, just kicking back and forth in the pool. I mean, she was world class. She won a bronze in the Pan Am Games when she was just a freshman. And then she had terrible health problems. She had headaches, and she had to quit because it was something about the body fat and stuff. I guess the athletes get real lean and they have all sorts of problems. There's some. Anyway, I'll not forget some of those athletes we had. But now it's really kind of crazy because Frank Thomas was here, Bo Jackson played baseball. And since that time, I think Tim Hudson was the only other big baseball guy that went through here, but we never did win a crown. We're hoping to. Anyway, you might see it when your time here in Auburn. All right. I was hoping more people would show up, but I didn't expect the full class to show up, man. I even got messages, do I have to come? Just responsible for the material. Do you got any questions about anything right now so far? Yeah.
7.2.5.
Okay.
It's a lossless dipole antenna is attached to source with a length of lossless 50 ohm coaxial cable.
A lossless, go ahead.
Lossless 50 ohm coaxial cable.
Right.
The source has an open circuit voltage of 100 volts RMS.
This is 50 ohms, okay, so then I have, oh yeah, okay. This is different volts. This is, VS is what?
100 volts.
RMS.
Yes.
All right, that makes a difference, go ahead.
And a source impedance of 50 ohms.
Okay, let me redraw this. Sorry. I'm gonna start with the antenna, and is that halfway?
Yes.
Okay.
Dipole length is 1/2 wavelength, and the transmission line length is 1.3 lambda.
This is the problem, and this is Z0, it's 50 ohms,
Yes.
and then we have a source resistance here of, how much? Okay.
50 ohms.
And then you've got this, and this is VRMS is equal to just 100 volts. All right, so this problem, this is a kind of classic problem. It's a little different than Wentworth's book's problem. Dr. Wentworth's book usually just isolates one simple facet of the problem. Here you got multiple things going on. You with me, class? Now, it's an exact half-wave dipole. For a half-wave dipole, the antenna impedance is equal to 73.2 plus J42.5 ohms. I'm gonna tell you one thing. Now, this is sort of the classic numbers, but the dipole impedance, if it's an exact half-wave dipole, the impedance depends on the actual diameter or radius of the wire. You all hear me on that? And it does change. The dipole impedance, this is like for an ideal case, very thin wire, you'll get that if it's exactly a half wave. I want to make sure I say this so everybody catches this. What they normally do with dipoles, they don't want that J42.5. That does nothing except irritates people. Y'all follow me? So if they shorten this antenna, and this is done classically all the time, if they shorten it so the length itself is equal to, instead of a half wavelength, 0.485 lambda, instead of 0.5 lambda, 0.485 lambda, about there, then Z antenna is just equal to 72 ohms. There's no imaginary part. So just by shortening it a little, you'll get rid of that reactive component. Do y'all follow me? Now that's desirable, that's done all the time. And the way they shorten it, well, if it's just a straight wire antenna that you tape down on a yardstick, you can take just toenail clippers and cut the ends down by a little bit and just see how that impedance changes. You can do this kind of stuff. I haven't done that. I did something like it years and years ago, but I haven't done it myself. I'm just telling you that that's sort of a classic. So that's what you'd really like. This is the problem at hand, where you have that. Y'all with me? Now, this is a transmission line. If we have a transmission line, what we need is the input impedance right here. Y'all follow me? We need the ZN of the transmission line. I'm gonna erase this. So, if y'all remember transmission line theory, if you have some load, a ZL, right? And you have a length of line, L, and an impedance Z0 here, then you want the input impedance Zn. Now, if you don't remember this exact, I understand that you don't use it as much as I do. The input impedance to that would be equal to Z0 times ZL plus JZ0. This is assuming it's lossless, times the tangent of beta L over Z0 plus JZL times the tangent of beta L. Y'all remember that, class? How many do, honestly? All right, this is the classic transmission line input impedance calculation. And you get, you'll see it over and over and over and over again if you're working in anything that has to do with electromagnetics or Wi-Fi and stuff like this. This is like the classic stuff for design. Right now, when you come down here, they said the length is equal to 1.3 lambda, right? Now, here's the thing, every time you go a half wavelength on a Smith chart, remember, everything repeats itself. You guys remember this? So you can literally subtract half wavelengths from this, and it's the same effective electrical length if it's lossless. So if I subtract one wavelength, which is two half wavelengths, I got 0.3 lambda. Do you all follow me on this? You might as well make it 0.3 lambda. That's what it really is as far as the calculations go. Y'all remember this? So now, I've made it that, but I need that input impedance. Now, when I look at this, I need that quantity beta L, right? Well, beta L, if you look at this, beta is 2 pi, right, over lambda times lambda. Well, lambda is 0.3 lambda in length. The length is 0.3 lambda, so it's times, you can call it 3 over 10 lambda. All right, that's 0.3 lambda, and the lambdas cancel. Right? And now I have 2 by 10 is going to be 1 by 5, and I have 3 pi over 5, and that's in radians. Now that's the argument beta L. All follow me in this class? All right. Now to get the input impedance, I do this calculation. My Z naught is equal to 50 ohms, and my Z load is actually equal to 73.2 plus J 42.5. There's more going on in this problem than most problems, right? So, can somebody do that for me? I can do it if you want me to on my calculator, or my computer, but if y'all can do that, by the way, this is where more mistakes are made, right? Doing this. Remember, that's radians. That's 3 pi over 5 radians. Now you can put it in degrees if you want. Multiply it by 180 and divide by pi. But tell me what you get for that, because this is probably the most important, or the easiest to mess up part of this problem. By the way, what did he ask for you?
Total average power radiated by the antenna and the VSWR on the cable.
This one. All right, we'll do that. First I need this. I'm so glad you asked. I gave these problems, this is out of an EMC book when I teach electromagnetic compatibility. These are problems that introduce you to a lot of calculations.
Using 14.39 at an angle, you want me to put it in?
Either one.
14.39 at an angle 79.56.
And give it to me in real imaginary.
.61.
Most of it's imaginary.
14.15.
Okay. Anybody confirm that? Get it? Okay. Now, at that point, we come over here, and now I'm going to redraw this circuit. I'm going to replace this part of the transmission from here over with that. So now I have a VRMS equal to 100 volts. Then I have 50 ohms here. And now I have that impedance, which is going to be 21 or 2.61 plus J 14.15 ohms. That's this impedance here. And what I need is this current, I. Now, this will be the RMS current, so I'm going to put down IRMS. And that's going to be equal to 100 over 50 plus this, plus 2.61 plus J 14.15 ohms. And now for this IRMS, you can just give them, they need a magnitude and an angle. But just the magnitude is the only thing I need here. Y'all follow me what I'm doing here? Just calculating the RMS current, not the peak current. In Whitmore's books, all the things are at I naught as the peak value. This is RMS, but it's gonna make things a little easier in a second.
1.84 and then negative 15.1.
Negative 15.1?
Yes.
Okay. Anybody else confirm that before we just move on? You got that? Now, if we didn't make any mistakes, that's the RMS current. Y'all with me? The peak current would be what? That times the square root of 2, wouldn't it? Right? Now, if you got RMS current, the nice thing is this. When we want total power radiating, that's what he asked for, right? P rad?
Yes.
For P radiated, if we have RMS current, I mean, normally it's what? 1/2 I naught squared times the radiation resistance of the antenna. Y'all remember that? That would be for peak current. I naught would be peak. If it's RMS current, it's just IRMS squared, magnitude of that squared. Maybe I better put magnitude here squared. And it's gonna be times R rad. Now, R rad is the radiation resistance of the antenna. If you look here, what's the radiation resistance? It's just the real part, right? It's just 73.2. The imaginary part you ignored. Y'all follow me? Imaginary part cannot radiate anything, only the 73.2. So it's gonna be I squared, or 1.84 squared. Then it's times 73.2 ohms. And you can give me that first.
247.83.
247.83 watts, right? Now, is that agree with the book's answer for the solutions?
The book says 43.1.
Watts?
Yes.
Then,
Total average power rating.
I think we did something. Must have done something. Oh, but now it's too large of an error. Round up. Almost 11. Or yes, it is. And which one was this?
7.2.5.
Last one. Lossless dipole antenna is attached to a source of 50 ohm. The source has an open circuit voltage of 100 volts. And the source impedance of 50, you got that right. The frequency of the source is such that the dipole length is 1/2. Wait. Then, this must be wrong here. Let me just see here. I'll do that calculation. This is an odd week. We got one class. Let me get this for you. Now I got it. This is called global attack. Can you give it to me again?
Yeah, 23.07 at an angle negative 5.43.
23.07.
At an angle negative 5.43.
All right. Can you also real and imaginary?
Yeah. Twenty-two point nine seven, minus J 2.18.
All right, if that's the case, and I'm assuming it is, then our current changes, because I'm assuming that's right. Then our current IRMS current is gonna change, and that's gonna change the whole deal. So that current is gonna be 50 plus, this is 22.97 plus J, or minus J, pardon me, J 2.19. And give me the IRMS current. Now we're talking about one. Well, maybe 1.2, I'm not sure.
1.37.
All right, now if that's 1.37 amps, then up here, he said it's 47.
Yeah, he said 43.1.
All right, well, then
That's still giving me 137.
yeah. Let me check this. I'm not, this calculation is the one that always gets people, usually because CL's got a real imaginary part. And that one, that kind of drives you nuts. Let me just do this. So, CN.
What was the answer? 44?
43.1.
I got 44.
For what?
Final answer.
Yeah, but I mean, what'd you get as the current? Or what'd you get as this impedance right here?
51.81 minus 40.6.
That's this is almost guaranteed the errors right there in that calculation. All right, if you got that, I'm going to just check it one time and confirm it. Now, I'm going to warn you about that calculation right there. ZL has a real and imaginary part, and it's times J. You all see it at the bottom. I promise you, these calculations usually are the culprit. Give me 1 second.
What did you get for these?
ZN.
Yeah.
That one.
Anybody else?
I got the same thing, but I'm not.
Yeah.
Like 60 watts.
You got it?
Yeah, I got the 22.
Say 105.
I got 9,638. It's, I guess it's close
Did you
enough.
get the right
Wait,
Square
you're
that.
you're squaring the whole.
Oh, I didn't
wire,
get power
not just
yet.
the real wire.
What's that? I couldn't hear.
Are we squaring the real part of the current?
Oh, no, just think the magnitude of it. It's IRMS squared.
8.46.
Yeah, that's what it is, just the magnitude.
Yeah, it's just magnitude, and then it's times the. All right, now,
Yeah, that's better.
Yeah, that's just right, that's 3 pi. Beta's 3 pi 10, right?
No, 3 pi. Well, beta L is 3 pi over 5.
That's better. That makes a difference.
beta L should be
Yeah, I was doing the same thing, I don't even.
Pi.
I didn't even catch that. I wrote it down as beta, so that's probably why.
All right.
That gives me what you got, I think.
I actually want to do this one. I'm gonna use this and I'll upload this thing so you can check. I got 22.97 minus J 2.186.
Dr. Baginski, I think we calculated beta L wrong.
What?
So when I touch on my calculator, I got 1.84.
I got 1.88
Yeah.
for beta.
When you do 3 power of 5,
But
hold on,
Yeah,
I don't know what I did.
beta is 2 pi over lambda. And the
Yeah.
length is just 3/10 of lambda, so the lambda is always canceled. So now I have 2 by 10 is 1 by 5, right? And so it's 3/5 times 5, that should be right.
Yeah.
Now, let me, I'm gonna go and finish this calculation. Hang on. So I got, is that what you guys got for ZN?
Yeah.
Yeah.
All right, now for ZN,
Wait.
that means I, and this is gonna be R in there.
Is it because length is 0.3 and not 1.3
No, it
lambda?
doesn't change it very much.
Okay.
IRMS is equal to, BRMS divided by ZN plus 50. And BRMS is 100. That means the magnitude is, I'm getting 1.37.
For the current?
Yeah.
And that means power P rad should be,
Okay, I got that number for P-Rad.
37.
Yeah, 137.
Yeah. What's it saying? It's 40 something.
I'm gonna radiate power 137.364. I got beta now.
What was the answer? What answer?
43.1.
I got it. They're using an L lambda over 2. So that ZN is just 73.2 J
Wait,
14.5.
say again?
He's using the L equals lambda over 2. For the
Beta L?
for the
Well, it
beta
ain't
L.
though. It's, the length is 1.3. So if that is the reason for the mistake, and some grad student finished that problem, not claiming, is that the guy who wrote this book is a very famous EMC fellow. He's dead, and if he works problems, they're right. But if they use lambda over 2 for the length of the transmission line, they're wrong. The transmission line is 1.3 lambda, according to at least the statement of the problem. So when you put in lambda over 2, you get the right answer. And the book has a mistake.
Sue.
The other one should have been right. I've checked most of these problems. Well, anyway.
Got it first.
I believe
7.2.
the answer we had there, the 1 point, I had a current of, I'm just telling you what the right answers are. The value for the current is 1.37 amps. Is that, yep.
So I didn't use the 73.2, but I used the real value of our ZN, the 22.97 that we calculated right there, and I got 43.1.
This is on me, guys. What you just said is the right thing, and I'm so sorry. I was assuming that was the current that's flowing in the dipole. That was my assumption. It's not that current. All right. The actual current that is flowing in the dipole is going to be greatly reduced because this is the current that's going in right here at the input, right here. But the current that's going to be developed there is not the same. This is a standing wave thing. So what you actually have to do, and you're absolutely right about this, is that if that was the current in the dipole, then what we did is right, but it's not. When we take a look at a transmission line, we erase this. And you have a transmission line, and it basically has a real and an imaginary part. And you know the current IRMS flowing here, then the only thing that can radiate power is gonna be the real part of that, of the actual input impedance to that. All right, now the thing is, the current, I was assuming that was the current in the dipole, it's not. So if you think about this part, right, that's, remember, when you have a transmission line by itself, a lossless transmission line, it doesn't dissipate any power. So all the power, the real power that goes in there is radiated. You all follow me on this, class? All right, what is the real power that goes in there? Well, it would be the power, or the real power, you might say dissipated, would be the IRMS squared times this value, R right here. And that real part is 22.97. So the actual power dissipated, or power radiated, PRAD, would be that IRMS squared times the actual real part of the input impedance, which is 22.97. And that is correct. That's on me. Sorry about that. I mean, we could get the voltage at the load. I'm just going to tell you this. We could go ahead and get the voltage at the load, then the current at the load. Then if we got the current at the load and squared it and multiplied by 73.2, we get the right answer, but it's easier to do it this way. Thank you. And that is the right answer, is it?
Yeah.
All right. That's on me. Now for the standing wave ratio, do you remember how to get that? Well, what is the standing wave ratio in your own words? Do you remember? Whenever they talk about a standing wave ratio, it's the ratio of the peak value of the voltage to the minimum value of voltage on the transmission line, right? If you have a short circuit on a transmission line, the standing wave ratio is infinite because it's actually a short. It goes to an absolute zero. So any voltage developed on it divided by zero is infinite. If it's an open circuit, it also goes to infinity. All right. But when it's somewhere in between, do you remember how to get the standing wave ratio? The VSWR, or the standing wave ratio, is just V max, maximum possible on a transmission line, over V min. I'm trying to refresh your memory on these things. Now, what is the voltage on a transmission line? V of Z in general, it's some V0 what? Plus, and then it's times E to the minus J beta Z, plus the reflection coefficient at the load times E to the plus J beta Z. Do y'all remember that? I'm just writing the equation in the phasor domain for the voltage if you knew the reflection coefficient. The reflection coefficient at the load is really what? It's Z load minus Z naught over Z load plus Z naught. Now, can you just give me that in terms of magnitude and magnitude? Now, ZL is 73.2 plus J 42.5, and Z naught is 50. Give me magnitude and angle for this one, too.
.372 at an angle 42.34.
All right. Now, when you look at this equation, I want to make sure I get this to everybody. You're right. See your eyes. This equation right here is an interesting one, and I'm not going to go through the proof, but the greatest possible value it can have, V max, is going to be just V0 plus in magnitude times 1 plus the magnitude of gamma L. We can play the game with these things rotating and stuff like this, but this will be the largest possible value. I can do it with a derivative of the magnitude. First you get the magnitude, take the derivative of the magnitude, set it equals 0, solve it. It'll come down to this, guaranteed. The minimum value zero plus, and it's gonna be 1 minus magnitude of gamma L. Are you with me? You remember this now, kind of? That means the ratio of the maximum to minimum is simply going to be 1 plus the magnitude of gamma L over 1 minus the magnitude of gamma L. So if you go ahead and do that calculation, it's 1 plus 0.372 over 1 minus 0.372. And that should be the Bismarck if you do it.
2.185.
2.185? Is that the answer?
That's it.
And we would have got that correct, even if we messed up the power rating, because we did have that, we did know the input impedance of that antenna. Now here's the kind of problem I could give you on a test. Hint, this is the kind of problem I could give you on a test. I could take the same problem, instead of making it an L over 2 damper, I could make it either a short dipole with a given impedance, or I could make it exactly 0.485 lambda, so the impedance would just be 72 ohms, no imaginary. Do y'all follow me in that class? And then I would ask for something, and here's, keep listening now. The gain, by the way, the directivity and gain for a dipole is 0.485 lambda in length versus 0.5 lambda. The gain and directivity are identical. You don't have to worry. So there's no change in the gain calculations. So let me just tell you why I'm saying that. Because you could get the P radiated the same way we just did. We would take the input impedance, the real part of the input impedance, and then multiply that by the magnitude of the RMS current squared. Do you all follow me on that? Now we have the radiated power. If I wanted the electric field at some given point, downfield, let me do it right here. I'll show you why I'm saying this, because I ask these kind of problems, and if you're paying attention to what I'm telling you, and you're thinking about it, you'll zip through this, and you'll have no problem. But if you're not, you're usually totally lost. And I've seen this, I mean completely lost, because there's usually something about these things, transmission lines and stuff, people, they'll mess up if they haven't done the problems. They just do this routinely. So now, I'm gonna come down, I'm gonna find IRMS, all right, and from that, I'm gonna get P rad equal to magnitude of IRMS squared times the real part of Zn on that transmission line, which is the resistance. You all follow me? The I squared R. Now that's the power rating. Now if I want the electric field, or say I want the average power anywhere downfield, if I want the average power density, now I get the total power radiated. Now you remember how I always tell you to do these, the way I think about it. Find the total power radiated, we just got it, right? Now we divide it by 4 pi r squared. That's the range to the target, to the place I want the electric field measured. You all follow me? Now that's the isotropic power density. Then I have to multiply it by the gain, and if the efficiency is 100%, you could just say the directivity, right? For a halfway dipole, and for a dipole, it's 0.485 lambda. The gain itself is going to be 1.64, slightly better than 1.5. Then it's going to be times that function cosine of pi over 2, cosine of theta over the sine of theta squared. Now I would give you that formula for gain. I don't expect you to remember that one. But I do expect you to at least have an appreciation for how you would do this problem. In other words, total power radiated, just take that by the gain. So for any angle, at any given range, you can find the average power density. Do you all agree with that? Now this is in the far field, so we can get this. Then I usually ask at a given range and at a given angle what the electric field is. This tells me if you have a complete understanding. So if I wanted the electric field at the point where this is the average power density, how do I get it? Do you remember?
Magnitude of E field over, is it AM?
Yeah, and let me get down the fundamental. The average power density is equal to 1/2 magnitude of the E field squared over eta naught, right? And so reverse engineering that, this would be equal to square root of 2 8 times the average power density. Do y'all agree with that? Now I've got the E field, I've got the power density at any point down target. I usually say power on target because I'm always doing radar problems. And there's targets out there you want to know what the power density is going to be that actually illuminates them. And if I want the magnetic field, what would I do? Anyway, just divide by 8 right? Now we've got everything. We've done everything in that problem. Yeah.
So for the IRMS, we're always going to use the Z naught or the ZN. The real for the Z.
The real part of
So-
the input impedance to the transmission. Because remember, this transmission line can't lose power. It's lossless. So the only real power that's going to be dissipated or launched, in a sense, it's not really dissipated, it's just, it turns into electromagnetic energy. It's going to be IRMS squared times the magnitude of IRMS squared times the real part of the resistance, because the imaginary part doesn't radiate any. The imaginary part, remember, anytime you have an inductor or capacitor with a plus or minus J any impedance, there's no power lost with that. It's simply what power is going to be stored in the field, then collapse back. Stored, collapse, that's it. The real part of the impedance will always dissipate power. And I do appreciate you catching me on that one. Anyway, and did you have another question? That's a good problem, by the way, because there's a lot of detail in there. It makes you think through a lot of different aspects of a real problem. By the way, that's a lot closer to a real world dipole problem than most of the stuff you see in Dr. Woodward's book. He just isolates small aspects of it and kind of here everything going together as a real problem. All right. Any other questions before? Now I'm going to get to, but I'm glad we did that. Get to what I wanted to talk about. All right. Today, I'm going to talk about, we've done the short dipole, the loop, we've done a small loop antenna, we've done multiple turn loop antennas, we've done the gain calculations, and now we're going to do something, we're going to talk about monopole antennas, which just means antennas where they're using an image of a source that is really, this is a mathematical way of solving problems easy by using this method of images. And instead of me just explaining in words, let me show you what I'm talking about. First, if you have a perfect conducting ground plane like such, right, and you put a charge above here, say at a height h, you have a charge plus q. You can imagine this. And I wanted to know, say, I wanted to know the voltage out here at some point, at some R, right? I want to know what this is. Well, and this is a question somebody might ask you just to hear the way, they want to see the way you think about it. Now, technically speaking, at this point, I don't think you've been exposed to the method of images. So the way to solve this is, you're going to solve the del squared of V equals minus rho V over epsilon everywhere around here, and match the boundary condition that the voltage here, because it's a ground plane, will be 0. You all follow? That's a tough problem. I'm going to tell you that because the only way that, if this is a point charge, this becomes a delta function, and when you solve this thing, you're going to get a long series answer. It's going to be a pain. I'm not going to go there. You know, there's 2 derivatives here. It'll be probably solved in Cartesian or cylindrical coordinates. And it's one of those things that in the graduate programs, you do these things all the time, this kind of a problem. That you realize the way the solution is going to go. There's one method to do it, by solving that. We don't do that. The mathematically accurate way, it'll get you the right answer, the easiest, is we assume, now think about this, if you have positive charge here, and this is a ground plane, negative charge we develop under here, that would have a profile like that for the charge density. Does that make sense to everybody? It'll attract it, and it has to. So, what they actually do is say that we can replace, or we can effectively say And what happens, don't worry about the ground charge or the charge developed on the ground plane. If we're at a height h, we can come down a height h and just put a negative charge at that same height. And then we can remove the ground plane. All right, this is the effective way to do it. Got a plus charge, put a negative charge below there, and we can say the voltage at any given R1 and R2, where R1's just the distance to this point, and R2's just the distance to the point where we want, is just the voltage from this charge plus the voltage from this charge, or minus the voltage, or minus Q over 4 pi epsilon naught. In other words, the voltage there, where I'm showing you, it would just be plus Q over 4 pi R1, and you've got to put an epsilon naught in here, and then it would be minus Q over 4 pi R2 epsilon naught. And that is the right answer, by the way. And that'll get you the right answer. That Q's a point charge every time. We can get the E field by taking the gradient of that, minus the gradient of that. Now, you don't have to worry about that, you're not gonna do that calculation, but you have to appreciate the way this problem breaks down is by using a method of images. It becomes trivial. Y'all follow? Now, so charges mirror that way. And if we have currents, I've gotta listen to me here. There's my ground plane. It doesn't have to be a perfectly conducting ground plane, but it's got to have it's got to be mainly conducting, all right? At the frequencies of interest. Now, if we have a current in the vertical direction, just follow me on this. I have a current I, and I'm going to say, if you think about the way current works, wherever the current's pointing at, this is going to develop a plus charge, and down here, there's going to be a negative charge, because it's the lack of charge. It should be there. Y'all follow me? All right, so if you come down here, that negative charge would be imaged by a positive charge. And then, for where the positive charge is, at that height, you come down, and now you would image a minus charge, right? Y'all follow me? The rationale behind this. Dr. Wilmore's book does discuss this. All right, so the negative images as a plus at a shorter distance, the plus images a negative at the full length below there. That means this effectively is imaging the current in the same direction, and this is important. The currents that are vertically oriented with respect to the ground plane will have an image current below there that is in the same direction. Do y'all follow me on that, class? Now, if you have currents that image, if you have horizontal currents, we'll call it I, then, and this is a ground plane, the way they image, just think of this. This is the plus Q, right? So below the ground plane here, at the same height above it, this was H, you'd go down H, you're going to have a minus Q here. And for this one, because it was minus Q here, now you're going to have a plus Q here. And they image in the opposite direction. So currents parallel to the ground plane will develop an image in the opposite direction. Now the reason these images are good for current and for charges, when I solve this problem right here, right, I don't need to worry about the ground plane. I can say everywhere above the ground plane, it's simply the radiated fields from this dipole superimposed with this dipole, regardless of the length of the dipole. And for this one, if I care about the electric fields anywhere in the upper half above that ground plane, I take the current here as if it was a single dipole and add it, or find the electric fields from it and add it to the electric fields from the image current. This is called the method of images. And one last thing, how would this image? If this is a perfect conducting plane, and I have a current like this, where this is going to be H1 and this is H2. How would this image? Just think about it for a second. Well, you know, the vertical component of that current is going to image in the same direction. Y'all agree? And the horizontal component will image in the opposite direction. So down here, what you effectively get is this. And that's the way to an image if it was something that was neither horizontal or vertical but had components above. The horizontal component of the current image is opposite, the vertical component images in the same direction. Do y'all follow me on this, guys? All right, now back to the monopole. After that little discussion. So here, and this is the way it's done in the real world most of the time when you see these big straight wire antennas. They are going to use the ground plane to develop an image current. They're gonna be half the length. If it was a half-wave dipole radiated, it would be a quarter-wave monopole would develop the same exact electric fields in the far field because it has the same current. So here's what happens. Instead of having a dipole like this of length L, if you have a ground plane, what they'll do is this. They'll have, to get the same kind of electric field pattern, they'll have this length be simply, this will be L over 2 in length. Whatever the total length of that dipole is, this will be L over 2. And that will cause an image current to be developed down here of the same exact shape and magnitude as on the half-wave upper dipole. Do y'all follow me on this? And I'm trying to make sense of this without spending too much time discussing just some of the ways to think about it. I wanted to give you some problems or show you how to do this. So, if we have a half-wave dipole, I want you to think about this. I'll go back there. If you have a half-wave dipole, you know that the actual electric field, and I'm going to write this down, if we're measuring at a given range R and angle theta, the electric field would be J times 60 over R times e to the minus J beta R times I naught would be the current at the base of that antenna. And then it's times, let me do it this way. Make this make this lambda over 2 in length, right here. So it's a half wave, and I don't have to make this expression really complicated. Then it's going to be times the cosine of pi over 2 cosine of theta over the sine of theta and the a theta direction. That would be the electric field. You all agree with me there? All right, that's the electric field at any given range and angle. It'll be the same for the monopole antenna. The only thing it depends on is this I naught value at the base. Now, when you take a look at the actual value, if that's the electric field, then I know the average power density here would be equal to 1/2 magnitude of that electric field squared divided by eta naught. I can write that down, but I don't need to. And I would say, and this would be true anywhere for any given R and theta, and I would say that the total power radiated would be equal to 1/2 magnitude of I naught, this is the peak value squared, times 73.2 ohms if it's an exact half-wave dipole. It would be 72 ohms if it was a short 0.485 dipole. Y'all follow me on this? And radiation resistance, R rad, for that, or I should say Z antenna, the antenna's impedance, if it was an exact half-wave dipole, was 73.2 plus J, 42.5 ohms. That's all true. Now, when we have, you might say the equivalent for a monopole, a half or a quarter wave monopole. Here's the ground plane. There's no ground plane over there, it's free space. Now we make the length of this dipole half that length, so this would be lambda over 4. This would be the length of a monopole antenna. All right. For the monopole antenna, if you find out the current going in the base, I naught, the electric field is the same. So for a monopole antenna, if you're at a given range R and an angle theta, the electric field will be the same as it would be for that halfway dot. Identical, because here's what happens. An image current is developed down here, and that image current will be identical to the current above there. It will make it effectively a halfway dipole. You all follow me? All right, the electric field's the same, so it's going to be simply J times 60 over R times e to the minus j beta r, and then it's going to be times the cosine of pi over 2 cosine of theta divided by the sine of theta in the a theta direction. That's going to be the electric field. You can get the H field just dividing that by a to naught if you want it, and it would be in the phi direction. Y'all follow? Yep. I try to race through this. All right. The power would be the same, but here's the thing. All the power is only in the upper plane. There's no power down here. You all follow me? Now, logically, if you think about that, the only way that can happen if the same current is there is if the radiation resistance or the dipole's impedance, the Z antenna, is exactly half that of a half-wave dipole. Do you all follow me? It would have to have half the radiation resistance because it's radiating half the power. The current's going to give me the same electric fields everywhere. Same power radiating the upper half plane, but zero down here, so the radiation resistance goes down by a factor of 1/2. That means for this, you would say the Z antenna right here would be equal to the 73.2 plus J 42.5 divided by 2. Now, and remember, P radiated, because of that, when we look at P radiated, right, for the monopole, this would be for the lambda over 4 monopole, it would be equal to the P radiated for the dipole divided by 2, or it would be equal to 73.2 divided by 2, because that's the radiation resistance of this, and then it's going to be times 1/2 times magnitude of I naught squared. That would be P radiated, because now, and it works exactly, it's exactly half that radiated by a lambda over 2 dipole, because it's a quarter wave monopoles above there. Y'all follow me? Exactly. The one difference is, I mean, the one thing you have to be careful about is now the actual directivity, the directivity for the lambda over 4 monopole is going to be 2 times the directivity for the lambda over 2 dipole. All right? And the reason is now there's no power radiating to the lower part of the plane. So when you do this, I'm going to just explain the reason for it. If you think about directivity, D max, and the way it's found, it's 4 pi divided by an integral of the normalized power, right, as a function of theta and phi. And then it's going to be times sine of theta, d theta, d phi. You at least recall that, right? And for the phi integration, it goes from 0 to 2 pi. That's over the entire horizontal plane. But now, if you think about it for a monopole, the theta integration only goes from 0 degrees to 90. Do y'all follow me? It's only going from straight up to the horizontal plane. There's no power, normalized power radiating below that. So that means this is only going to be over half the angular integral from before. Do you all follow me on that, class? And that'll double that. It means that for Dmax for a quarter wave monopole, it's actually 2 times 1.64. So it's going to be double that. That's what? 3.28. Okay, that would be Dmax. Can you all follow me? Now, that's the maximum directivity. If you take that times the normalized power density, which would just be the cosine pi over 2 sine theta squared, then you get the directivity of a monopole antenna anywhere above the ground plane. I mean, in the upper half plane. That would be the directivity. And the rest of those calculations kind of fall out. Once you have the directivity, if you know the radiated power, just take the radiated power. Well, the way I like to do this is, when you find the radiated power, it's limited to the upper half plane, right? You've got that, you can divide by 4 pi r squared. That would be for an isotropic radiator. And I know in the back of my mind, I'm always thinking, well, you're assuming it's gonna radiate into the ground. Now, this is the way the equations work. The doubling happens with the directivity. Now the directivity is double the directivity of the half-wave dipole because of the monopole. So you'll still get everything correct. And I'm gonna say one other thing. If ever you get a little fuzzy about it, you see this electric field? That only depends on the current. The current only depends on the Z antenna right here. Do y'all follow me? So if I give you a voltage source and it's a monopole antenna, it's exactly quarter wave, or however I specify. The only thing you use the Z antenna, which is half that value, right? Divide that into the voltage, and now you get the current. Once you have that current, you can get this electric field. Y'all follow me? That electric field is the same. The only thing that depends on the current, it's the same whether it's a quarter wave monopole or a half wave dipole. Everybody follow me on this? Now, if you have the electric field, you can get the power density automatically, right? 1/2 times the magnitude of the electric field squared divided by 8 and 9. And you'll see, after you do a few problems, how it all comes together. All right, that is how monopoles and antennas are really solved. You take whatever you know about the full length dipole, short dipole, half wave dipole, whatever, cut the length down by 2. The radiation of the Z antenna is halved, and the directivity goes up by a factor of 2. When you work a few of these problems, it'll become clear, right? Now, there's a monopole problem in those problems I gave you. Do you remember which one it was?
Yeah.
I want to do that one next. And find one that, if you can, that's a half wave. I mean, it's a quarter wave.
Okay.
Not a short wave. Now, let's put these ideas to the test. Go ahead.
A lossless quarter wave monopole antenna is situated above a perfectly conducting ground plane and is driven by a 100 volt, 300 megahertz source.
Hold on for a second. So it's got plus to minus 100 volt RMS?
It doesn't say on this one.
All right, 100 volt, and go ahead.
300 megahertz, that has a source impedance of 50 ohms.
So we've got 50 ohms here, source impedance. Go ahead.
Determine the total average power radiated. Also, the magnitude of the electric field broadside to the antenna.
Okay. They want,
And the power density at a distance of 100 meters.
okay, so they want P rad. They want an E field, is that right?
Yes.
At some R equal 1.
Determine the magnitude of the electric field broadside to the antenna.
But,
Oh, I think it's the same 100 meters as the
all right, so,
power density.
all right, so it's 100 meters. They want E, and they want the average power density, 100 meters, right?
Yes.
R equal 100 meters, all right? What problem is that?
7.2.2.
So, I'm gonna show you probably the way I would think about this. I need the equivalent impedance of that antenna, the ZN, right? You see, it's a monopole, so I know if it was a full lambda over 2, I would take 73.2 plus J42.5. But now we divide that by 2. So here's the electrical circuit for this. I've got a voltage source that's plus or minus 100 volts, and if it doesn't say RMS, it's assumed peak. Then I have 50 ohms of source resistance. Now, here's my antenna. My antenna is gonna have an impedance of 73.2 plus J 42.5 divided by 2. That's my antenna impedance. And I need to find this current, I. And this is gonna be a peak current. So, can you guys do that for me? That is what, 36 something, plus J 21.25. But if you do that, can you give me I naught there, which is just gonna be 100 divided by this total impedance, which is 50 plus that Z or Z halfway divided by 2. And just give me the magnitude.
1.121.
121 amps. Now that's peak though. Right? Now, if we have that, and we want the electric field broadside, now just think about it. Now I want it at an angle here that's 90 degrees. Do y'all follow me? At 100 meters. So we want the electric field 100 meters away from the base of the antenna. The angle would be 90 degrees. Do y'all agree with that? If the antenna is vertically oriented? Well, the electric field would be what? Technically, it's J60 times I naught. That's the I naught we found over R, right? R in this case is 100 meters, isn't it? I'm gonna put down 100. They only want the magnitude, right? So I don't need to write the e to the minus J beta R in here. And times this, well, the cosine of pi over 2 cosine of theta over the sine of theta at 90 degrees is 1. So this whole thing will become 1, which is very nice. It's nice to know a priori so you don't have to punch this in your calculator. You might get a crazy error bubble. Let me just see it. Let's see. Sine of 90 degrees is 1, so that's not going to cause it to divide by 0. So then I get cosine 90 degrees is 0, right? 0 times pi over 2 is 0. Cosine is 0 is 1, 1 by 1 is 1. It makes sense. That means this electric field is 1. It's going to be really, in magnitude, it's 0.6 times, because it's 60 over 100, times 1.121. And if you give me that, let's check and see if we get that right.
Yeah, 0.673.
Is that his answer?
Yeah, that's it.
0.673 volts per meter. Now, remember what I told you about the power? Right. Once we have the electric field, how do we get the power density? Right. Then, that's right. The average power density would be 1/2 times, it's going to be the magnitude of the E field squared divided by eta naught. In our case, it's 1/2, right? Magnitude of 0.673 squared divided by 120 pi. That will be right, I think. Are you following me what I'm doing here? Working a problem helps with this stuff. Six times 10 to what?
So 60 milliwatts.
6 times 10 to the minus 4 watts. Is that about right?
Yes. Yeah. He has 0.602 milliwatts per meter squared, which is this.
Yeah, all right. I'm not gonna fight you on that. All right, that's fine, all right. And then for the total power radiated, how do you get that? Pay attention to this part. Now remember, the radiation resistance, the real part of the antenna impedance is the thing that's key for power radiated. So for this one, total power radiated would be 1/2 times I naught, which is 1.21 I'm sorry, 1.121, my bad. 1.121 squared, and then it's times the real part of the antenna impedance. Well, the real part of the antenna impedance is 73.2 by 2, because it's a monopole. So it's going to be 73.2 divided by 2. And if you can give me that, or 73.2 divided by 4, and then multiply it by 1.121 squared,
Practically 23.
23? 23 watts, is that the answer?
Yes.
Y'all follow me on this one? Now, when you do a few more monopole things, you can do this for the short dipole, you know, just double the length. If they have a monopole antenna that's short, you double the length and then get the electric fields as if it was a dipole, twice the length of the monopole. But I'll give you some more problems so you can work and get a good feel for this. Okay. Now, and I only have 5 minutes. I wanted to do arrays or star arrays. I'm not going to have time to do the whole thing. Matter of fact, let's see. Is there another monopole? Yeah.
He also asked, what is the direction of this electric field vector with respect to the ground?
Perpendicular. It has to be, because remember I told you if you have an antenna currents this way, the electric field is always going to have an E theta component, more or less, and when you're at 90 degrees, it's vertically oriented, up or down. You all follow me on that? So that's, he should say vertical at the ground. I don't know if he does or not.
Yeah.
All right. Is there another monopole one? I'm not going to have time to do the array stuff. If I had an extra 15 minutes, I would, but I prefer not starting on that and only going a little way into it and having to redo it again. So we'll do another.
The quarter wave monopole antenna of problem 7.2.2 is replaced by a 1/5 lambda lossless monopole that has an input impedance of 20 minus J50 ohms.
All right. So now we got an antenna that's got, this is a monopole, right?
Yes.
And it's
just
lambda
wants
over 5?
It just wants the total average power radiated.
All right, but it's lambda over 5?
Yes.
And they say this is still a monopole, and they say the Z of that antenna is what?
20 minus J50.
Minus J50, okay. And then what the total power radiated?
Yes.
Now, think about this. They gave us the antenna impedance, right? If you look back at the prior problem, here's what we had, a source voltage that was plus or minus 100 volts. And that was actually a peak value of voltage that had an impedance, an internal impedance of 50 ohms. And then we have this, 20 minus J50, all right? And they want the total power radiated. Now, take a second and just look once you've done that. The only thing that we want to really know about is how much power is being dissipated by that 20 ohm portion, because that's the radiation resistance of that antenna. You all follow? So after we find the current, which would be 100 divided by 50 plus 20 minus J50, right? So this antenna current would be 100 divided by 70 minus J50. I don't know what that's going to be, but I care only about the magnitude. If you can give me that. 20 and 50 is 70. That's what I got, 70. Just give me the mag. You can give me the angle too if you want, but I need the magnitude.
1.162.
1.162, and you might as well throw in the angle. It's positive.
35.54.
Okay. Now we get the total power radiated to your ad. It's simply 1/2 times the magnitude of this, which is 1.162 squared, I naught squared, times the radiation resistance, which is 20. So, I don't know what that is, but it looks like it's about 10, maybe 12.
13.5.
13.5 watts, is that right?
Yes.
Okay. Now, I'm out of time. Does anybody have any questions? And thank you for coming. I know, this is like one class out of a week, but I appreciate you coming here. I'm going to give you a few more. Matter of fact, why don't you do all those problems in that lot? I don't know if there's a few more I didn't sign, but just make sure you do all those problems. And when we get back on Monday, we got the 4th coming up. Not,
Monday after.
so really, we're gonna have 1 week of classes and another day off.
I don't think we have class Monday either.
Yeah, we have Monday too.
Wait.
That-
Hold on.
oh, yeah.
Wait a second, we have Friday off, right?
Monday.
We have Monday off too?
Because, yeah, for mini master exams.
Wait, we have this Friday and then following Monday off?
Yeah.
Oh, God,
This is a really long weekend.
this is insane.
And it's all supposed to be
Who
mini
came up
master
with this
finals.
calendar? I mean, it's like, why don't we just throw a month away? So, following Monday, how am I gonna cover all this material?
One hell of a mini master.
All right, on Wednesday, we're gonna pick it up. Please be ready to move. I'm gonna give you a little
About the
reading. I'll give you some problems. When is the semester over?
The
Mini master?
29th.
No, I want.
The
full
whole
10 weeks.
summer?
I think it's like the 29th or 30th.
Are you serious?
It's like August 5th is our last.
Please
August
tell me
5th
it's
is
somewhere in
six.
August.
August what?
Like August 5th is our last exam.
Yeah.
So we're done basically at the end of July then.
Basically.
Let me just think for a second. So June is basically shot,
Yeah.
thanks to the calendar committee that decided, oh, what the heck, have a few more days off. That's bizarre though, that many days off.
Yeah.
I think it's because of Juneteenth. Because last year they pushed it because they missed it. And so they pushed it into like the fall semester.
Wait, there was a Juneteenth last summer?
Yeah. Well, not last summer. They pushed it into the fall because they missed it. Because it became a holiday after.
Yeah, that, yeah.
And so, still.
We have to have so many class days, we can get away with losing 1 or 2, but to lose like 45 class days, so we got July. All right, let me just think. I'll be done with the antennas and another 2 lectures, I think. Then we have to do microwave, and we have to do EMC. I can do it. I can make that happen without you guys crying. But it seems like we're missing way too many days. I mean, I don't ever remember a summer where you had this many days off in a 1 month span of time.
That's a lot. This is a lot of days off.
I mean, it's ridiculous. Some students, oh, it's great. It's really not when you think, you gotta know this material, you're paying to learn this material. And it should be in a way that, allows coherency and some, you might say, some amount of appreciation for having very little time gap between classes, because, it's very hard for students. When I was a student, if I took one class, like a class, like in say, vector mathematics, and then I didn't get to apply that to anything for an entire year, I have to relearn all that stuff. Unless you continually use it, isn't reinforced and you don't remember it that well. At least that's for me. For you guys, you're getting like weeks now, where there's nothing new coming at you. So the next time we meet is next Wednesday. Isn't that right?
Yeah.
Yikes, full week off. Well,
2 lecture days.
for what it's worth, please do the reading assignment I give you, and give you some more problems. Thank you for keeping me on track. That's problem today. That was on me. Guys, anybody need to see me?